Anybody have any homework questions you want me to go over?
3A and 2D.
Okay. Okay. So let me draw what's going on here. So it's launched at 25 meters per second, 30 degrees below horizontal, and takes 3.4 seconds to hit the ground. So it's launched from above the ground, and it's launched initially at an angle like this, where this is 30 degrees. And the path always is going to be a parabola that starts out with the slope of that starting velocity. So it's going to go like this, like that curved path. And it takes 3.4 seconds to hit the ground. So how high was it launched from? I didn't bring a calculator, so hopefully one of you guys has a calculator and can punch this stuff in when we need it. So we're going to start by making our 4 choices, our time equals 0 instant, time final instant, and then the coordinate system orientation and location. I'm going to put the origin on the ground right underneath where it's launched from. That's pretty much my standard way to do it. And the y-axis is pointing up. And then my time equals 0 is going to be the instant that it's launched. And time final is going to be the instant right before it hits the ground. And now we can list out what variables we know and want. So for the first part, we're trying to figure out what this height is. Okay, so let's just go through the list. Do we know time final? So that is, do we know what the stopwatch says after we click it off? Yes. Yes, we do. That's 3.4 seconds. Do we know the acceleration vector? In free fall, we always know that. So 0, negative 9.81. Now, the initial position, we know one thing about it, and one thing about it we're trying to find. We want to figure out what the initial height is. So we're trying to figure out P-I-Y. Okay, and we know from where I put the coordinate system, based on where I put the coordinate system, that P-I-X is equal to 0. Okay, so remember that those position vectors are just the coordinates of the object at that instant. So in this case, you can see that the coordinates of this point here, this starting point, is 0 for x, and we don't know what it is for y. We're trying to find that. Then do we know anything about P final? Well, we don't know the horizontal P final, but we do know that PFY is equal to 0. again, because of where I put my coordinate system. Do we know anything about the initial velocity? That's where we can use the fact that it's 25 meters per second at an angle of 30 degrees below horizontal. So VI, to get that, here's our coordinate system. And we can put the tail of that velocity vector at the origin. And the magnitude of this vector is 25. So we can call this 25 times the cosine of, you can go clockwise 30 degrees. So that would be the cosine of negative 30 and 25 times the sine of negative 30. You also could go counterclockwise and call it 330 because it's 30 degrees short of making it around to 360. Can someone tell me what those numbers are? 25 times cosine of negative 30? 21.65? Oh, and then this one, maybe I can get that, 12.5 negative. Okay. So 21.65 negative 12.5. And then do we know anything about the final velocity? What? It would be, right. So that's right before. So it's not zero, exactly. Exactly. So we don't know the final velocity. So this is what we're working with. Let's see now. So we can go through those equations. We know we're trying to find PIY. So we know it's not going to be any of the x equations. So the possibilities, I guess, are VFY is equal to VIY plus AYTF, or PFY is equal to PIY plus VIYTF plus 1/2 AYTF squared, or 2AY times the quantity PFY minus PIY is equal to VFY squared minus VIY squared. Okay, so the first one doesn't have PIY in it, so that doesn't work. The second one, it has PIY, and then everything else in it is known, so that one will work. This one we don't know VFY, so that one won't. So plug into this equation, you get that 0 is equal to PIY plus negative 12.5 times 3.4 plus 1/2 times negative 9.81 times 3.4 squared. So PIY, if I do this algebra, is 12.5 times 3.4 plus 4.905 times 3.4 squared. Can someone punch those out? I moved those to the other side of the equation. I did maybe a couple of algebra steps here, but so I guess you could think I have negative PIY is equal to negative of this and negative of this, and then I took the negatives of everything, so they all get positive. Can anyone plug that in for me? erase it. What? Okay.
I got 99.2.
Okay, that sounds a little familiar. Maybe let's go with that. So 99.25? Is that what you said?
2018.
Okay. 99.2. Okay. Yeah, seems in the right ballpark. Any questions about that one? And then let's do part B also. So part B says, how far does it travel horizontally before it hits the ground? So now we're trying to figure out this distance. Is there any reason that we have to choose new instance for our time equals 0 or time final? No. Remember, those are always based on instance where you have information and instance when you're trying to find information. And so the only time you have to switch is when the question asks you for something at an instant that wasn't one of your instants in the first part. This time it's still asking for something that happens at the end of this motion when it right before it hits the ground. And so these instants still work fine. So we can use all the same choices. And what that means is everything that we knew before and anything that we calculated in part A is stuff that we know now. So now we know we still know time final is 3.4. We still know the acceleration vector is 0, negative 9.81. Now we know all of the initial position. We know that that vector is 0 for x, 99.20 for y. We know that PFY is equal to 0. And this time we're trying to find PFX. And we know VI is equal to positive 21.65, negative 12.5. Okay, so let's see. I think we can just go straight to this equation. PFX is equal to PIX plus VIXTF plus 1/2 AX TF squared. So PFX is equal to 0 plus 21.65 times 3.4. And now here's the one where you have to be careful because you're used to putting in negative 9.81 for A. But remember that that's only the y component of A. The x component of A is 0, so this term goes away if you're talking about the x's. And can someone multiply those out for me? 73.61 meters. Okay. Any other homework questions you want to see? Okay, well, let me just I want to do one more example problem, and then I want to talk about something specific related to this. So let's say that an object is launched 40 degrees above the horizontal, with a speed of 10 meters per second. And from a height of 1 meter. And we want to figure out first, what's the height of the object at its highest point. And then we want to figure out how far the object travels horizontally before it hits the ground. And then last, we want to calculate the displacement vector from the location where it's launched to where it hits the ground. Okay, so to draw this, it's launched from a height of 1 meter. And initially it is 40 degrees above the horizontal. It has a speed of 10 meters per second at that instant. And then it's going to follow a parabolic path like that. And so the first thing we're trying to figure out is what is the height when it reaches this highest point. Okay, so first I have to choose where I'm going to put the origin, how the coordinate system is going to be oriented, and my time equals 0 and my time final instance. I'm going to put my origin on the ground below where it's launched from. And my time equals 0 instant is going to be the instant that it's launched. And what's going to be my time final instant? Well, the thing is here, we're trying to find information specifically when it gets to the highest point. So the only way to do that is to choose one of your instants to be there. So our time final has to be the instant it reaches the highest point. The thing that's interesting about this example problem is when we get to parts B and C, we're going to have to switch, exactly. So this is the instant it reaches the highest point. And now we'll go through what we know and what we want. We don't know the elapsed time. We do know the acceleration. That's 0, negative 9.81. Do we know the coordinates of the ball at the instant it's launched? Where I put the coordinate system, it would be 0 for x and 1 for y. So this is 0, 1. Do we know the coordinates when it reaches the highest point? Well, we're trying to find the y coordinate, so I'm going to put PFY over here. And we don't know how far it travels horizontally. That's something we would have to calculate. We're not asked for that right now, so I'm going to leave that off. Then the initial velocity. So to do that, I'll put the tail of that initial velocity vector at the origin. This angle is 40 degrees. The magnitude of that vector is 10. And so that initial velocity vector is 10 times the cosine of 40, 10 times the sine of 40. And so that's 7.66, 6.43. And then this is the one we've been waiting for. As soon as you hear something about the highest point, you know you're just waiting to write down the fact that the y component of the velocity is 0 at the highest point. So do we know anything about VF? We don't know the x coordinate, the x component, but we do know that VFY is equal to 0. In fact, by the way, we kind of do know VFX because there's never any acceleration in the x direction. So that's just going to stay the same the whole time. But if you write that down, it'll make it look like equations work that aren't going to work. So just leave that off always. Okay, so let's see. Is there anything that we can figure out here? I think the equation that should work is 2ay times the quantity PFY minus PIY is equal to VFY squared minus VIY squared. Let's see, so PFY is in it. AY we know, PIY we know, VFY we know, VIY we know, so yeah, this one will work. So 2 times negative 9.81 times the quantity PFY minus 1 is equal to 0 squared minus 6.43 squared. And remember, don't put in the negative 6.43 and then square that. We're going to square the 6.43 and then subtract. Okay, that minus sign has to stay outside of the square. So this is negative 19.62 times the quantity PFY minus 1 is equal to 6.43 squared is 41.34, so this is negative 41.34. Now you can divide both sides by negative 19.62, and you get PFY minus 1 is equal to 2.11. And now add 1 to both sides, and you get that PFY is equal to 3.11 meters. Any questions about that? Okay, so now we're on to part B. And for part B, we're trying to find horizontally how far does it travel before it hits the ground. So is there any reason we have to change one of our instants?
Yeah.
In this case, we have to change at least one of our instants has to be the instant where we're trying to calculate stuff. So our time equals 0 can still be when it's launched. But our time final this time has to be the instant before it hits the ground. Just before it hits the ground. Okay, so what that means is, we still have the same time equals 0, so any of our initial stuff still applies in this second part, but any of our final stuff, that doesn't apply anymore. That was talking about a different instant. Okay, so let's just go through the whole process of listing these out again. We still don't know how long it takes. We know that the acceleration is 0, negative 9.81. We know that the initial position is the same as it was before, 0, 1. The final position, what do we know about the final position? Anything? Yeah, we know that the y component is 0. So Pfy is equal to 0, and Pfx is what we're trying to calculate. The initial velocity is the same as it was before because that's at time equals 0, which is what it was before. So this is 7.66, 6.43. And then what about the final velocity? We don't know anything about the final velocity because we're not talking about the highest point anymore. We're talking about a later time. So this is it. This is what we have. Okay, so if we're trying to calculate Pfx, we know that we have to use one of the x equations. And so the question is, do any of the x equations work? The Vfx equation, that doesn't work because there's no Pfx. The Pfx equation doesn't work because we don't know time final. And the 2ax equation doesn't work because we don't know Vfx. So nothing works. And so what do we do when no equation works for what we're trying to find? Yes, exactly. So we want to calculate time final. Okay, so now the question is, what equation works to find time final? I think the one that should work is Pfy is equal to Piy plus Viy Tf plus 1/2 Ay Tf squared. So yeah, Tf is in it, and we know Pfy, we know Piy, we know Viy, and we know Ay. So this will work. So 0 is equal to 1 plus 6.43 Tf minus 4.905 Tf squared. So how are we going to solve this for Tf?
Quadratic.
Yep, that's right. Quadratic formula is really the only way to do this unless somehow you could figure out how to factor it. So this is A. This is B. and this is C. And let's see. Yeah, I answered some different questions in my notes. Can somebody who has the quadratic formula programmed in, could you plug these into your calculator and tell me what you get? About times, you always want the positive one. So we're always going to throw away the negative one. Yes?
So because we're really just talking about the instant before, we can attribute the PFY to 0.
Yes.
Even though it's like a minuscule, I'm sure.
Yes, exactly.
That's
I mean, okay, so.
I'm sure it would just be.
No, I mean, that's a really good question.
Sorry, Samantha, like just, yeah, specific.
No, I mean, I remember thinking about that over and over again when I was first taking physics. Really a more accurate way to think of it, but it's just a little more confusing to describe, is imagine this motion happening and the ground isn't really there.
Okay.
The ground is like a laser, you know.
Got it.
And so you're going until it hits that level, but the ground just isn't going to stop it.
Okay, got it.
Yeah.
So we're not just accounting for that velocity, basically.
Right. Okay, so now that we have this time, now that's one more thing that we know in here, and now we can use the equation that says Pfx is equal to Pix plus Vix Tf plus 1/2 Ax Tf squared. So Pfx is equal to 0 plus 7.66 times 1.45 plus, what's Ax? 0, yep. So remember that the acceleration, the x component of acceleration is always 0 on these. And so what do you get if you multiply those two together?
11.11.
Okay, 11.11. Okay, so. Okay, and then the last thing I asked for, part C, was, okay, what's the displacement from the location where it's launched to the location where it hits the ground? So remember, the displacement is just, what?
Final minus one.
Yep, the position, like at the later instant that you're considering, minus the position vector at the earlier. And so at the later, we know we have an x component of 11.11 and a y component of 0. And then the earlier instant we're considering is at time 0, and that is 0, 1. And so the displacement vector is 11.11 and then negative 1 for y. And in other words, what that means is this is the vector that goes from here to here. So that blue vector is our displacement vector. Any questions about that? Okay, so now I want to bring up something. I said this before, that there are a couple of times, I think 4 total times in this class, where most likely, so in this class I said intuition is helpful. There's a lot of stuff that we kind of understand intuitively about this, but there are a few cases where your intuition is probably wrong. You just kind of grow up thinking the wrong stuff about how stuff works. Who remembers what the first one was that I talked about, the first common misconception? I showed a video related to it. Yep.
Gravity is the same.
That's right. So everything falls at the same rate unless there's air resistance changing the effect. And so now here's the second one. So common misconception number 2. So it's often believed that the horizontal motion of an object affects how quickly it falls. So I think people kind of have this intuition that the faster something is moving horizontally, the longer it'll take to hit the ground. Okay, and there are some cases where that make sense. Maybe a frisbee is the best example. You know, if you just drop a frisbee down to the ground, it hits the ground quickly. If you throw it horizontally, it takes longer to hit the ground, and that's a real thing. Okay. But that, again, is just because of air resistance and air effect. The rotation of the frisbee keeps it oriented so that it has a lot of air resistance. And so, really, if you ignore air effects, so let's say, in fact, the horizontal and vertical motions are totally independent of each other. And so here's an example of what I'm saying. So say that you have 2 people back to back. One fires a bullet out of a gun. And the other person drops a bullet at the same time. Forgot to give this guy eyes. Don't shoot a bullet without eyes. Okay, so this guy fires it. This guy drops it. I think it's pretty universal that kind of everybody, before you learn about this, would assume that the bullet that you drop is going to hit the ground before the bullet that's fired horizontally out of the gun. But the truth is that they hit the ground at exactly the same time. So a bullet fired horizontally hits the ground at the same time as the drop bullet. Okay, so gravity is pulling just as hard on it, even though it's going, fast, say over 1,000 miles an hour. Gravity is pulling just as hard on it, and so it'll hit the ground a long way away. But if you have a way to carefully accurately measure how long it takes to hit the ground, it will be at the same time as the one that's just dropped straight down. Question?
Will the pressure matter? Because it comes to like at a higher pressure when you drop it?
Yeah, it doesn't matter. Yeah, it doesn't matter. Okay, so what I have is a video of the Mythbusters people doing this experiment. And so I'm gonna show you them doing this experiment. One thing you're gonna see is on their first attempt at it, their only attempt at it, they get it super, super close to exact, okay? But in their measurement, the one that gets shot from the gun does hit slightly later than the one that's dropped. So like, what's the deal with that is a question you might ask. And I'll do a calculation that shows what I think probably happened there. You have a?
Pretty sure bullets are also designed to fall slower nowadays. I don't know if that's true. I don't know if that's true either. So I guess I'll just leave it at that.
Bullet drop is the same at the same height, regardless of its fire.
Yeah. Okay. All right, let's watch the video. Okay. Wrong button.
So what's your theory?
Let's just do the calculation to show, why they should be exactly the same. Okay, so a calculation shows that they're the same. And so I'm going to do both of these from a height of 1 meter, just because, makes the math simple. So let's say that we have them dropped and fired from a height of 1 meter. Okay, so first we'll just do the dropped one. And this we can just do as a 1D problem. There's no, the thing isn't traveling in a plane, it's just traveling straight down along a line. So this is just a 1D free fall problem. I'll choose my time equals 0 to be the instant that it's dropped. And time final to be the instant just before it hits the ground. And so if this is the ground, this is where it's dropped from. I'm going to choose my 0 position to be on the ground and my positive direction to be up. So negative is down. And this height is 1 meter. So then I'll list out what variables I know and what I'm trying to find. Time final is what we're looking for. We're trying to calculate that. The acceleration, since my positive is up, the acceleration is negative 9.81. The initial position is 1 meter in the positive direction, so PI is 1. P final is 0. It's just being dropped, and the person is just standing on the ground that isn't moving, so the initial velocity is 0. And we don't know the final velocity. Okay, so is there an equation that works with that? I think the one that we can use is PF is equal to PI plus VITF plus 1/2 ATF squared. So 0 is equal to 1 plus 0 minus 4.905 TF squared. So 4.905 TF squared is equal to 1. Divide both sides by 4.905 and take the square root, and you get the TF is equal to plus or minus 0.4515 seconds. And this is time, so we want the positive, and so that's the answer, 0.4515 seconds. And now we're going to do the calculation for the bullet that's fired. And what you're going to see is that even though this is a two-dimensional problem, we end up reducing the problem to this exact equation again. And so the answer has to be the same. It comes up in exactly the same way mathematically. So this time, So there's the muzzle of the gun. And the bullet is initially fired horizontally. And I'm going to say that its speed, just for simplicity, is 1,000 meters per second. And the path that the bullet is going to take is going to be a parabola. So it'll go something like that. Obviously go out a lot farther, but anything in projectile motion either travels along a line up and down or it travels along a parabola. The question is just how stretched out the parabola is or, compact the parabola is. And I'm going to, like usual, put the coordinate system on the ground right underneath where the thing is at the start of the motion. So there's my coordinate system. And my time equals 0 instant is going to be the instant that it's fired. And the time final instant is going to be the instant right before it hits the ground. And then we'll list out what we know and want. We're trying to find TF again. The acceleration vector, since it's projectile motion, is 0 for x, -9, computer. -9.81 for y. The initial position is 0 for x, 1 for y. The final position, we don't know the x final position, but we do know the y final position is 0. The initial velocity, okay, so the initial velocity, if you draw out the coordinate system, and put the tail at the origin, that vector is going to be horizontal with a magnitude of 1,000. That's in the positive x direction. And so this velocity is just going to be positive 1,000, 0. And we don't know the final velocity. And so is there an equation that we can use to find TF? Yeah, we can use the one that says PFY is equal to PIY plus VIYTF plus 1/2 AYTF squared. And if you plug that in, you get 0 is equal to 1 plus VIY is 0 minus 4.905 TF squared. And so, now you can look above, and we were in exactly that same position with the drop bullet. So it really can't turn out any other way. So now you get 4.905 TF squared is equal to 1. So TF is equal to positive 0.4515. Okay? So now the question is, why was the bullet fired in the video slightly later, very little.
Is it later or earlier?
The one that was fired hit later in the video, yeah. I mean, it could have happened either way. If they would have angled it down a little bit, it would have hit earlier. I think they must have angled it up. I mean, you can imagine, like, all they could do is use a level to measure to try to get it as level as possible with the top of the muzzle. That doesn't mean that there's not slight differences in, the angle between the tube in there and the top or whatever. Question?
Is this assuming the speed that the bullet exits the muzzle of the gun?
Yeah.
Okay, so then if they took it at the time it's fired and then as the other bullets dropped, it would have also gone off, right?
That's true too. Yeah, that's true. Although, I mean, I guess you'd have to calculate just how long it takes to, yeah, right, to get through the tube of the muzzle, yeah. So now we're going to do this problem again. And I'm going to make the angle that it's fired 0.1 degrees above horizontal, okay? That's so little. I mean, you absolutely can't see that with your eye. So 0.1 degrees above horizontal. Okay, so I'm going to draw this picture exaggerated just so you can tell what the angle is I'm talking about. So let's say that it's fired like that, and that this angle is 0.1 degrees. And then the path it's going to follow is going to be like this. And I'm going to put the coordinate system the same place I always do. And then my time equals 0 is going to be, again, the instant that it's fired. My time final is going to be the instant right before it hits the ground. I'll just say when it hits the ground. Okay, so again, we're trying to calculate time final. We know that the acceleration is 0, negative 9.81. The initial position is 0, 1. The final Y position is 0. And now for the initial velocity, we're going to have to calculate this. So, okay, if our coordinate system is like this, and our initial velocity vector is like this, that's curved. Okay. Then that initial velocity vector is going to be 1,000 times the cosine of 0.1 degrees and 1,000 times the sine of 0.1 degrees. Can someone calculate those for me? So the first one is basically going to be 1,000. Okay, so 998, okay. 999.998. So not quite, but pretty close. And then what's the second one?
1.745.
Okay, 1.745. Okay, so that's the initial velocity vector. And we don't know the final velocity, so this is it. And so the same equation is going to work again, the one that says PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. And so 0 is equal to 1 plus 1.745 TF minus 4.905 TF squared. And again, we can use the quadratic formula for this. This is A, B, C. And if you plug that into the quadratic formula, the two roots that you get are negative 0.307. That's negative, so we don't care about that one. And then the positive one is 0.663 seconds. So like 0.1 degree difference from horizontal made it take 50% longer or something like that. Yep.
Could you theoretically just have done this, like, by taking the seconds that it was off and plugging it
Yes.
into the time final?
Yes, yes.
And adding it to, like, the seconds that it took?
Yes, exactly. So yeah, you could do that. So if you wanted, yeah, but don't do it. Yeah, right. Yeah, totally. Because you would just calculate what T final you wanted. You'd say it's, I mean, if you added that on, it would be what did they say? 39 milliseconds. So that's 0.039 seconds, I think.
Yeah.
So that would be 0.48, let's say 0.49 seconds, you know?
And then you would get the angle
And then,
theoretically? Or like you would.
yes, you'd have to use inverse trig to do it. And in this class, we're not doing that, but
Just out of curiosity.
yes, exactly. You could do that. And it would be much smaller, you can see, than 0.1 degree. Anybody have any questions about that? Okay, let's stop there, and I'm just going to give you a bunch of problems to work on, and if you have questions on any of them, we can go over them on Monday, so bring any questions you have on Monday. And okay, that's all.